that this is a classic problem. It is a classic problem. We've been talking about weak acids, weak bases, strong acids, strong bases. And so we just basically have a blob of stuff here, and you're supposed to say which one has the lowest pH, most acidic, which one has the highest pH, most basic, right? And so my suggestion to work this sort of problem is to go one by one and to say what you have kind of out there to the side. So ammonia, NH3, it's like, remember that first homework, we're like, okay, so is NH3, is it going to accept a proton and become NH4 plus, or is it going to lose a proton and become NH2 minus 1? Those are your two choices. So hopefully you're like, oh, I think it would pick up a proton and become NH4 plus, and you'd be right. So actually, you can find NH3 under the heading of a weak base. So I put WB there. Okay. Now, the next thing, we basically have a salt. This ammonium nitrate is a salt. We see it ionizing or dissolving into water, and it gives you ammonium, NH4 plus, and it gives you nitrate. Now, the thing about it, do you recognize that nitrate, to pick up a proton, NO3 negative, it's going to become HNO3. HNO3 is a strong acid. It's not going to be a proton acceptor. It won't do that. It won't form a strong acid. One of the things, I have a slide coming up, basically, it always goes from strong to weak. That would be going from weak to strong. But, so that nothing's going to happen there. I'll put a little X there. Nothing's going to happen. Okay? The other thing, the ammonium salt, yeah, it's a possibility. Can NH4 plus, can it kick off a hydrogen, bless you, and form NH3 neutral? Yeah, it can. Okay? So actually, but I'm going to say that that is the conjugate of a weak base. Let's see, conjugate, CONJ of WB. Okay? I should say conjugate acid of a weak base. Okay, so it's going to do that to a certain extent, but it's a weaker acid than NH3, ammonia, is a stronger weak base than that is a weak acid. Because we talked about conjugate acid-base pairs. Okay, so already be thinking, if it's a base, okay, or excuse me, that base, it's going to have a high pH. That conjugate acid of a weak base, it's going to have a lower pH. It's going to be on the acidic side of neutral. Of course, the first one's definitely going to be on the basic side of neutral. So that's kind of what you do. Looking at the next one, formic acid. Looks like it could kick off a proton, definitely. I'm going to put weak acid there. We could find formic acid in our Ka tables for weak acids. Nitric acid, okay, that is one of the biggies. That's a strong acid. Okay, so that's really going to probably be at the top of our, with our lowest pH. Okay. Then we look at, this is another salt here, the salt of sodium formate. Okay, so basically it dissolves in water, and you get the Na plus. Let's see, how do I say this? Yeah. Na plus, if Na plus is going to hydrolyze water, picture this. Na plus plus an H2O molecule. If it's going to act like a base, be a proton acceptor, or hydrolyzed water, I guess I should say, it's going to end up on the other side as NaOH. You're going to have NaOH on the product side. That's a strong base, NaOH. So that is a non-player. That one's not going to do anything. Now look at this right here. That formate ion, if you look two slides above, can you see where the formate ion is actually the conjugate base of formic acid? Okay, so this actually, I'm going to say conjugate B, or base, of weak acid. And the fact that it's a conjugate base means it's going to be on the basic side of neutral, right? Conjugate base of weak acid. Sodium nitrate. Again, it's a salt dissolved in water. Okay, again, sodium, is it going to go be sodium hydroxide? I don't think so, because it would be going to something strong. Nitrate, is it going to form nitric acid? No, I don't think so, because nitric acid is a strong acid. So actually, as it turns out, neither one of these are players. That thing's going to be totally neutral. And then the last one, let's see, what should I say? I'm going to put neutral next to that one. Okay. The last one, potassium hydroxide. Do you guys remember clear back? We said actually that is a strong base. SB. Two types of strong bases. If for every mole of salt you dissolve, you get 1 mole of the hydroxide ion, strong base. Alternatively, if for every 1 mole of, and I think the ethoxide ion does this, for every 1 mole of your strong base there, if it can hydrolyze a water molecule like ethoxide can, it's a strong base too. So let's take a look at what we got. Let's see, the first one, weak base. Doesn't it seem like, well, let's do it this way. What color didn't I use yet? This one should be the highest pH. Does that make sense? Strong acid will be the lowest pH. Okay. Then after our strong acids, we should start to look for weak acids. If we're going to go from what's going to be the next pH after a nitric acid. So we only have 1 weak acid. So formic acid actually is going to go next. Okay. Then we should look for conjugate acid of weak base, which actually is the second one up there. Okay. Let me go on to the next slide since we've kind of digested all that. Okay. So rearranging them. The lowest pH to the highest pH. Strong acid, strong base. In between, we have a couple of weak acids. That formic acid, HCOOH, that's formic acid. You would find the Ka on a table. NH4 plus. Now remember, the NO3 minus, that's actually a spectator. The thing giving non-neutral pH is actually this NH4. We said that was the conjugate acid of the weak base, specifically the weak base NH3. Then we go neutral, okay? That salt, sodium nitrate, neutral. It's like Switzerland. Because the conjugate acid and base for those are strong acids and bases, and it's not happening. Then we have a pair of weak bases. The pair of weak bases, actually, the one that's closest to neutral would be the conjugate base of the weak acid. So, let's see, this one right here. Sodium, again, is a spectator ion. The thing that's making your solution basic is the formate ion. Okay. That, we said, is a weak base. Or I think I just was saying, it's a conjugate base or weak base of the weak acid, formic acid. And then NH3, full-fledged, you can look up on, you'll find a Kb value for ammonia. Oops, sorry. You'll find a Kb value for ammonia. Okay, and then we top off with a strong base. So you're going to want to be able to kind of sort through those solutions. So we spent some time earlier in part 5 looking on either side of the reaction arrow or the equilibrium arrow and looking for things that differ by a proton. Those are pairs, conjugate acid-base pairs. And for every acid-base reaction, basically you have 2 pairs, pair A, pair B. okay? So you should be able to find them. So let's take a look at finding pairs. Of course, hydrochloric acid, sodium hydroxide, strong acid, strong base, respectively. But if we look for the proton, the things that differ by a proton, we can kind of start to find pairs. So, for instance, looking at the knowing that HCl is going to break apart into H plus and Cl minus, sodium hydroxide is going to break apart into Na and OH minus, thus the AQ there. Your salt on the other side, NaCl, is going to also be broken up into Na and Cl. So if we look for something that differs by a proton, if you focus on your chloride species, okay, here we have it differing by a proton. HCl on this side is acting as a proton donor. Over here, it's acting as a proton acceptor, if we were to go back to the other side again. The other pairs we have is the OH minus and the H2O. OH minus and the H2O. They differ by a proton. Okay. Here it's acting as a proton acceptor, so the OH minus is acting as a base. Over there it's acting as a proton donor, so over there, if this were a two-way arrow, it would be acting as an acid. Okay. So this is your two sets of conjugate acid-base pairs. By the way, if we were to just kind of pair out the spectator ions, both the chloride ion and the sodium ion are spectators. So we end up with the net ion equation of, it's like kind of the opposite of the autoionization of water. Okay, let's look at another pair. This one, because we're going to be using it a lot with our titration problems, this is called acetic acid. Acetic acid. You might recognize it because actually on the product side, this thing right here, I don't know if you remember, CH3COO negative is actually the acetate ion. Okay, so that's sodium acetate. So we have acetic acid. It happens to be a weak acid. And sodium hydroxide, of course, is a strong base. And it always goes from stronger to weaker. So if we look at to find our acid-base pairs, there they are. So one acid-base pair, conjugate acid-base pair, is the acetic acid, CH3COOH, and the acetate ion, conjugate acid-base pair. The other acid-base pair actually is the hydroxide ion from sodium hydroxide and the water molecule on the other side. Again, sodium is a spectator, so the net ionic equation is shown below there. Last one. So NH3, we just used before. You guys put a WB next to ammonia. Okay, so that's a weak base. HCl, strong acid. Okay, kind of show what's going on here with regard to the acid-base, conjugate acid-base pairs. The NH3 and the NH4 plus differ by a proton. That makes them conjugate acid-base pairs. I like to think of it as the chloride ion has a hydrogen over here. It loses a hydrogen over there. It differs by a hydrogen. Those are the other acid-base pairs. I kind of feel like you guys have been doing this. Taking out on either side of the arrow or equilibrium arrows, things that differ by a proton. So let's take a look at these. These will be due on Wednesday. So Thursday, we're keeping on track with our schedule, and we will be doing titrations. So, but we did titrations before, right? But this actually, we did strong acid, strong base titrations in Gen Chem 1, I think. In Chem 2, we are going to be doing weak acid and strong base titrations. All right, here we go. I think anyway. I'll have to double check that. So this is part 5. That doesn't look right. This is part 4. That's why. There it is. Okay. So this gives you CH3COOH. You should start to know that that is acetic acid. This gives you acetic acid, and you're going to react acetic acid with a certain number of things, either water or ammonia or the chloride ion or the nitrate ion. So to me, I actually probably would have 4 different equilibrium. So if we pick on A, what they're saying is, does this make sense? Will acetic acid react with water, and what will it form? Well, if acetic acid is acting as a proton donor, okay, it's going to kick off a hydrogen, and it's going to give it to the water molecule, which will act as a base, okay? And to me, that seems reasonable. Okay, that totally seems reasonable. Okay, which of the following bases, these other things, A through D, are going to act as bases, will acetic acid proceed the furthest? And so that seems reasonable. Look at B then. Does it see, what will acetic acid do with NH3? Okay, NH3. Again, acetic acid is going to be the proton donor. NH3 is going to be the proton acceptor, NH4+. That seems reasonable also. I think when it says the furthest, I'm going to add this to my comments here. Basically, no pun intended again, you're going to look for, how would this go? You're going to look for the weakest, I guess. Look for formation of weakest acid base. Because whatever's weak over there must have been stronger over here. Oops. The next one looks like this. That's funny. Oh, I did write some other stuff. So reactions will always favor from strongest to weakest, or strong to weak. So with this one, actually 7 and 8 are very similar. Notice you have the answers to 7 in the back of your book, which isn't the back of your book, which is under doc sharing, right? So you have the answers to 7 under doc sharing. It says use this table to predict whether these reactions will go from left to right, or will the right to left be favored. And the one that's going to be favored is the direction where you have the strong going to weak. So the first one, yeah, looks to me like it's going to go back this way. I agree with the birthday boy. Okay? So take a look at those, and this one is like the same way, similar to 7. All right. Now we're back to buffered solution. So when you guys did your experiment with red cabbage last Thursday, that first hood had buffered solutions, pH, 3, 5, 7, 9, and 11. So they were buffered solutions. So the thing about a buffered solution that you count on is that, and I really picture it this way, so just bear with me. Okay, basically, if this is a buffered solution, okay, I can add like this slide says. I can add H plus, and it will neutralize it. I can add H plus, and the pH will remain constant. It won't budge. I can add OH minus, and again, the pH won't budge. That's a buffered solution. It's kind of like buffering against pH change. So in order for that to be the case, you're like, really, how come, if you add the hydrogen ion, if you add H plus, your pH is going to go down, right? If you had the hydroxide ion, your pH should go up. Well, how does that work? And the reason that works is because basically in that pot, you have the hydroxide ion to go ahead and use up, or I should say the hydroxide ion. You have something, some sort of acid, that if you add hydroxide, it'll use it up. You have some sort of base, that if you add acid, it will use it up. So the third requirement of a buffered solution is that those things that are swimming around there to go ahead and either remove the additional hydroxide, or remove the additional hydrogen ion, they can't interfere with each other. They need to be able to coexist. Coexist. So those are your three requirements for a buffered solution, just kind of logical requirements. You need something to go ahead and absorb your base, something to go ahead to absorb your acid. And what works really well to have in your beaker to combat either one of those scenarios is actually what we've been talking about. Swimming around in that beaker, you basically have a pair, an acid-base pair that is a conjugate acid-base pair. So, here we go. This is the HH equation. I call it the HH equation because sometimes I don't want to pronounce Henderson-Hasselbalch. So if you hear me say HH equation, that's what it is. So I'm going to go ahead and put it over here. I think for your Unit 4 exam, you do not have an equation sheet. If you had an equation sheet, this would be on it. So this just means you'll be using it enough for example problems that you want to memorize this. This only works for buffered solutions, or specific to buffered solutions. Okay, it's called the HH equation. So the pH of your buffered solution is equal to the pKa of, remember, buffered solutions have a pair of conjugate acid and conjugate base swimming around in there. So whatever your acid is, not the Ka, but the pKa. Remember, to get the pKa, you take negative log of the Ka if you need to. Okay? Plus log base 10, and we put the base in the top. Usually I don't say conjugate base. I just put base because I know it's a conjugate acid-base pair. In the bottom, we put the molar concentration of the acid. That's it. That's the HH equation, Henderson-Hasselbalch equation. So, of course, the brackets means molar concentration of a buffered solution. And actually, this can be obtained by looking at your conjugate acid-base pair and rearranging the Ka expression. All right, so there's your Henderson-Hasselbalch equation, blue box. I'm going to show you another form of the HH equation. And in order to do that, let's look at the molar concentration of your acid and base. Of course, molar concentration is moles per volume. Okay, so we have moles per volume of your base, moles per volume of your acid. Okay, but they're the same volume. So we could go ahead and substitute in the molar concentration of your base, moles per volume, molar concentration of acid, moles of acid per volume. And of course, the volumes are going to cancel. So we get this other kind of nice little version of the HH equation, and it looks like this. Where basically for buffered solutions that are buffered with the conjugate acid-base pairs, it's the pKa of the acid plus log base 10 of the number of moles, variable n, moles of base divided by moles of acid. And again, this is conjugate acid-base pair. And there's the pKa of the acid. So it kind of depends which form, depends on your problem, which form works for you. They're both the HH equation. Okay, so in order for this HH, or it's easier to write, the Henderson-Hasselbalch equation for buffered solutions to be valid, we need to assume that the weak acid that's there is you're gonna keep, relatively speaking, you're not gonna use all that much of it up. The amount of ionization that the weak acid undergoes is negligible. The amount of hydrolysis that your weak base undergoes is also negligible. And we talked about the common ion effect. And actually, in this case, for a solution that's prepared with a conjugate acid-base pair, the presence of each other work with the common ion effect to make this basically the case. So it's kind of like, it's just itching to be a buffered solution if you have a conjugate acid-base pair. All right, so you have a buffered solution that somebody's prepared. It resists pH change. You can add acid, you can add base to it. It's going to fight that change. So can you see, according to the Henderson-Hasselbalch equation, that the ultimate pH of your buffered solution is really just kind of driven by the ratio of your base to your acid? Why? Because this is a constant, right? You get that from a table. What you have access to vary is the molar concentration of your base and your acid. So that's what's going to drive your pH to a certain extent. Buffered capacity, it kind of makes sense. Buffered capacity just means, again, if you're kind of the visual person like I am, is you're dumping in your acid, your base, trying to make it budge. Okay, basically you are going to hit a capacity. Okay, so the buffer capacity is basically its ability to fight pH change. And the capacity will depend upon the ratio, okay, and the concentration. So I think I have some notes for how to optimize your buffer capacity. So if you want to optimize your buffered capacity, basically you want this ratio to be as close to 1 as possible. I'm going to put an arrow there. I'm going to say it should approach 1. Okay? The log of 1 is 0. The log of 1 is 0. Okay? So if you do get that kind of nice buffered solution where the molar concentration of your conjugate acid and your conjugate base are the same, then actually your pH is equal to your pKa. So that's like the best. The other thing that gives you buffering capacity is you don't want to be too wimpy on the molar concentration of your acid and base. Okay? What this says is that the larger the molar concentration, assuming that you're able to go ahead and keep them similar, so your ratio is 1, the more buffering capacity it has. Makes sense. So I said that you want to approach 1 with the ratio of your molar concentration or your number of moles of base to your acid. If this gets, how do I say, if this becomes greater than 10, or if it becomes less than 0.1, okay, which means basically you're kind of outside the factor of 10. Your buffering capacity is not very good. So here we go, 2 forms of the Henderson-Hasselbalch equation. How to know that you have a buffered solution with a conjugate acid-base pair, and how to know what the pH of that is. All right. So when it comes time to go out and find your pairs, your conjugate acid, conjugate base pair, to go ahead and make your solution that you can dump acid and base in, and it will resist pH change. What you want to do then, since you're going to approach 1 here, and this term becomes 0, okay, what you want to do is basically find a weak acid or a weak base where the pKa is similar to your target pH. And this says that you also, in terms of buffering capacity, you don't want to get any weaker than 0.1 molar, even if they are similar. Okay, so there's 2 ways actually to go ahead in the same vat to get your pair, your conjugate acid-base pair. And we're going to talk about one way today. One is to literally mix some of this and some of that. Of course, this will be your conjugate base, this will be your conjugate acid. That's one way. The other way is even more interesting, and we'll talk about this on Wednesday, to basically force some of your conjugate to form the other thing by a strong acid or a strong base. I'll show you how that works. So let's look at the first one first. All right, so if I was going to draw a little picture, let's kind of been talking about, look for our acid-base pairs here. Here's my vat or my beaker. Okay, it says how many grams of sodium acetate. So look, I'm going to dump in CH3COONA. That's sodium acetate. Of course, the thing of interest here is this, CH3COO-. The acetate ion is the conjugate base of a weak acid. And then it goes on to say that actually down here in my vat, I have 100 mils, 3 sig figs, of 0.125 molar acetic acid, CH3COOH. Now when they give that the molarity of the weak acid, assume that that is like before any ionization happens. Do you think we can get the Ka from the for this from the table? I think we can. And we'll want to. Okay, so that's sort of what we got going on. How many grams of this do we need to add? That's our, I'm going to put over here weak base. And this is our weak acid. So if I was kind of putting things on our HH equation, we're basically in this scenario, we're going to have to find the Ka of acetic acid, CH3COOH, and this is going to be our acetate, CH3COO-, and of course that again is our CH3COOH again. That's what we have going on. What else it says is, do you see our target is to produce a buffered solution of pH 5. That is this. That's our target pH. So we're given this. We can look this up. Look up. And if we don't have the pKa, remember that we can get the pKa from the Ka by applying the log function. So that one's taken care of. Do we have the molar concentration of acetic acid? Yep, that's that 0.125 molar. Okay, and we don't have the molar concentration of the acetate ion. So that's kind of what we have going on here. I think I'm going to stick to my PowerPoint slides now for a minute. No ice table. No ice table for this one. So if you were to look up the Ka value for acetic acid, you would find that it's 1.8 times 10 to the negative fifth. We don't need the Kb this time for the acetate ion, but we could find it because, remember, for a pair like this, Ka times Kb is equal to Kw. So actually in my notes, I knock out what the Kb is. If we needed the Kb for the acetate ion, because of its relationship with acetic acid, it would be 1.0 times 10 to the minus 14 divided by Ka, 1.8 times 10 to the minus fifth. Kb is equal to 5.6 times 10 to the minus 10. So before I plug into the HH equation, I kind of want to show you one more way to kind of manipulate the HH equation that might be helpful. Oops. Before I do, one more thing. So, but this, in my new kind of form of the HH equation, we will need the pKa. So, of course, to get the value for pKa for acetic acid, we take negative log of the Ka for acetic acid, 1.8 times 10 to the minus fifth. So we got a pKa of 4.74. So what this says in red is, the fact that our pKa 4.74 is close to our target pH of 5.00. Yeah, it's pretty good. It's a good choice. Okay. So here's the HH equation. And actually, we could rearrange it, okay, by, it looks like, how do I want to describe this? By subtracting pKa from both sides. And then we can get rid of the log. We get rid of the log by taking 10 raising this, 10 raised to this power is equal to 10 raised to this power. We do the same thing on either side of the reaction arrow, or, equal sign, sorry. It is legitimate. So 10 raised to this power is equal to 10 raised to this power. Now the cool thing about this one, 10 raised to the log base 10 of that is actually, and I think we used this trick before, this thing is actually going to be now the molar concentration of the base, molar concentration of acid, is equal to 10 raised to the quantity pH minus pKa. And that's my other form. I just kind of wanted to show you where that came from. It's not even really its own legitimate new form. But the molar concentration of the base by the molar concentration of the acid is equal to 10 raised to the pH, the target pH, minus the pKa, which actually we got as 5.00 and 4.74 respectively. And I think I have a thing coming up here. We could go ahead and do one more kind of thing here. Instead of the molar concentration of the base, we could say the moles of base divided by the moles of acid, conjugate acid-base pair, in a buffered solution is equal to 10 raised to the pH minus the pKa. And actually, it's this one that we're going to use this time, and I'll show you what I mean. Okay, so back to the problem. Oh. Okay. So I'm going to, instead of using molar concentration, I'm going to go with moles. in part because they want the solid mass of sodium acetate we want to dissolve. So I know moles of acetate, that's probably better than molar concentration of acetate. So to get moles that are running around of acetic acid originally, I take the volume of acetic acid, which was given. Actually, there's a decimal after that 100. The volume, and I took the molarity, which is 0.125 moles per liter. And then, of course, I need to go ahead and get it from milliliters to liters. Oh, yeah, and the third term. So the moles of acetic acid are 0.0125. So here in a minute, if we use this form of the Henderson-Hasselbalch equation, that number goes right there. And of course, we know the target pH was 5.00, the pKa was 4.74. So now we know everything that we need to know, kind of, to get to the moles of base. Okay, so the moles of base are equal to the moles of the acid, which we just got, times 10 raised to the pH minus pKa. So in our particular problem, the acetic acid sodium acetate buffer, it looks like this. Where I actually brought my calculator today. This is the only problem we're going to do. We're not going to sign the problem. So 0.0125 times 10 raised to the quantity, 5 minus 4.74, and quantity is equal to, all right. Now, we're not quite done yet. So that's the moles of the acetate ion that you need. That's the moles of acetate that you need. So now we're back to kind of a Gen Chem 1 problem, where how do we get that moles of acetate out of sodium acetate? You know, and we need grams of sodium acetate. Okay, so you'll need the molar mass of sodium acetate, and I think I did it aside here. But if that's the target moles of acetate we need, recognize that in every 1 mole of sodium acetate, we have 1 mole of acetate present. That third term is the molar mass of sodium acetate, which you still need to show that work. This is the molar mass of sodium acetate. So that should do it for us. Looks like we need to round according to 3 significant figures. Okay, so the mass of sodium acetate you need to weigh up in order to get the moles that you need according to your HH equation of acetate ion is 1.87 grams of sodium acetate. Isn't it weird how sodium acetate like has the cation at the end? Isn't that weird? Like, that is just so weird. And that's your answer. So in order to prepare a buffered solution at pH 5.00, given that volume and that molarity of acetic acid, that's what you need to add according to your HH equation. Okay, so let's take a look at this problem. This problem will be due, this is actually on your last slide, but you guys should be able to do this one now. And the other problems aren't very, I know it's your birthday and all, but there aren't very many. Your other problems shouldn't take you too long. And doing one problem will lessen the load for your Friday, what you have to do. Okay, so that finally is what I've been trying to keep. This is the one. So see how similar this is to your the problem we just did? Instead of acetic acid, actually it's formic acid. Formic acid is HCOOH, so the formate ion is without a proton. Okay, so again, it gives you, it gives you molarity, so it doesn't give you volume. So this time, you're going to be using probably this one. You're not going to go to moles. Okay. and because it doesn't ask for grams, it just says what should the molar concentration of your conjugate base be. I think that might be my only hint. Nope, I have something else here. I just kind of drew some things here. So your target pH is 4.06. Your pKa, remember you can get it from your Ka. So take the negative log of this to get your pKa. The molar concentration of your formic acid was given 0.366 molar, and you're supposed to come up with the molar concentration of your base. You don't have to do that Chem1 stuff that we did with the sodium acetate. You just want the molar concentration. Okay? So that's it, those two. Wait, this and those other three.